knowledge extractor for 3-round interactive proofs. Let me just quickly get this out of the way. So this is nothing new, no parallel repetition, also no multi-rounds in there, but it's going to be the basis of our result. Then I will explain what goes wrong when we try to generalize this approach to the parallel repetition of these kind of interactive proofs. And then I will present our solution for these issues. First, working on the 3-round case, and then generalizing further to multi-round interactive proofs. So to set the stage, let us consider a relation R, which is simply a set of statement witness pairs. So the statements are typically denoted by X and the witnesses by W. And you can think of a statement X, for example, as a group element, and a witness would be a discrete logarithm for this specific group element. But relations can be of any form. And an interactive proof is a prover between, or a protocol between a prover and a verifier. They interact for a couple of rounds. The prover is given as input both the statement and the witness, and the verifier is only given as input the statement. And at the end of the protocol, at the end of the interactions, the verifier accepts or rejects the prover's claim that it knows a witness. So actually the goal of such an interactive proof is for the prover to convince the verifier that it actually knows a witness for this public statement X. And in this work, we only consider public coin protocols. And that basically means that all of the messages going from the verifier to the prover are challenges, C1 up to C mu, which are sampled uniformly at random from some challenge set. And in every round, the challenge set can be different. So these interactive proofs have a number of desirable security properties. And we will be focusing on knowledge soundness. Informally, an interactive proof is knowledge sound if a dishonest prover that does not know a witness cannot succeed or almost never succeeds in convincing a verifier. So that's one of the main properties that we would like these interactive proofs to have. More formally, knowledge soundness is defined in terms of a knowledge extractor. A knowledge extractor is an algorithm that is given as input a statement X and black box or oracle access to a prover P star attacking the protocol. And the goal of the knowledge extractor is, given this access to the prover, to extract the witness from the prover. And the knowledge extractor should be efficient. And this basically means that if a prover succeeds with large enough probability in convincing the verifier, then the knowledge extractor can extract a witness from this prover. Therefore, the prover must actually know a witness. So this is the way to formally define knowledge soundness. And this will also be our work to construct certain knowledge extractors for parallel repetitions of interactive proofs. There are a number of figures of merit that are of interest. So for instance, the success probability of the prover P star. You can imagine that if this prover succeeds with larger probability, it's going to be easier to extract a witness out of this prover. So this epsilon denoting the success probability is going to be an important figure of merit. And then we also have the knowledge soundness kappa, or the knowledge error kappa, which is informally the cheating probability of a dishonest prover. So basically, we aim for this knowledge error to be as small as possible. And so even more formally, the standard definition of knowledge soundness states that an interactive proof is knowledge sound if there exists an extractor with exactly these properties. So if the prover P star succeeds with large enough probability, so larger than the knowledge error, then the knowledge extractor is capable of extracting a witness in a runtime that is inversely proportional to epsilon minus kappa. So then we have this informal or this lemma that it is actually sufficient in our analysis to only consider deterministic provers P star. It's not completely obvious from the previous definition, but it's relatively straightforward to prove that this is indeed the case. And this will significantly simplify our analysis. So therefore, from now on, we will assume the prover P star to be deterministic. And in particular, this means that the first message of the prover will always be the same. So if you are able to prove that an interactive proof has knowledge soundness or knowledge error kappa, And this kappa is, for example, 1/2. That's typically not sufficient in practical applications. So you want to reduce the knowledge error down to some very small value. And there are a couple of ways, generic techniques to do that. The first one is sequential repetition. So instead of just running one invocation of the interactive proof, you can just repeat it sequentially. And this reduces the knowledge error from kappa down to kappa to the power t, where t is the number of sequential repetitions. This is very intuitive. This was also what you would expect, and this is well known. The downside of this approach is that it reduces the number of rounds. Sorry, it increases the number of rounds, of course. An alternative approach is to perform these repetitions in parallel. So then you don't increase the number of rounds. And you can immediately see that what happens is that the size of the challenge set increases from n to the power t. Instead of sending one challenge, you immediately send, or you send a factor of t different challenges, each for one for each of the parallel invocations. And the hope is also that for this parallel repetition, we would have a strong knowledge error reduction from kappa down to kappa to the power t. Well, unfortunately, this is not the case, and there are actually a couple of counterexamples that show that you cannot attain such a strong result in general. When you restrict, for example, to public coin protocols, as we are doing in this work as well, then there is a strong there is a weak parallel repetition result that shows that parallel repetition reduces the knowledge error from kappa to the power t plus this non-negligible term. And so the goal of this work is to actually get rid of this non-negligible term, so to get a strong parallel repetition result. And we do this for a very rich class of protocols, which are special sound interactive proofs. So for special sound interactive proofs, we actually show that you do not get this non-negligible term nu, and you really get a strong parallel repetition result, reducing the knowledge error from kappa down to kappa to the power t. So what is this special soundness? Special soundness is yet another notion of soundness, and it is typically much easier to handle this notion. It's easier to prove that an interactive proof is special sound than to prove that it has knowledge soundness directly. So the easiest case is 2 out of n special soundness. So in a 3-round interactive proof is 2 out of n special sound if there exists an efficient algorithm that takes as input 2 colliding transcripts. So here we see A, C, Z and A, C prime, Z prime. Those are protocol transcripts for these 3-round protocols. They have the same first message, but a different challenge. C and C prime should be different. And from these 2 transcripts, we can extract, if we can extract a witness from these 2 transcripts, then efficiently, then the protocol is said to be 2 out of n special sound, where n is the size of the challenge set of this interactive proof. It is very well known that 2 out of n special soundness implies knowledge soundness with knowledge error 1 over n. And also there are some well-known generalizations of this notion of special soundness. So you can also go to k special soundness, where instead of 2 transcripts, you need k transcripts. There we see that it implies knowledge soundness with knowledge error k minus 1 over n. And there are also multi-round generalizations of this notion of special soundness. And we know that these generalizations also tightly imply knowledge soundness. So let us look at a very simple knowledge extractor for 3-round interactive proofs. So let pi be such an interactive proof, k out of n special sound. It has 3 rounds. And let p star be a deterministic prover that attacks this protocol. And then p star can actually be seen as a deterministic function that takes as input the challenge c, and it outputs a bit string z. So z is basically the third message of the protocol. And the first message of p star is always the same. It's always a, because it's deterministic prover. And p star is successful if this transcript a, c, z is accepting. So if you look at such a prover in that manner, you can actually summarize its properties by means of this binary vector. So this 0, 1 vector indexed by the challenges C1 up to Cn. So a 0 entry is actually corresponds to a challenge for which the prover fails, and a 1 entry corresponds to a challenge for which the prover succeeds. And epsilon, the success probability of the prover, is actually the fraction of 1 entries in this matrix or in this vector. So then we have this very simple extraction algorithm. We start by sampling entries from this vector until a 1 entry is found, until we have this first accepting transcript. Well, this first step takes time, expected time 1 over epsilon. Then we continue. We ignore the entry that we have already found, and we are going to continue sampling entries until a second 1 entry is found. This takes expected time at most 1 divided by epsilon minus 1 over n. And the minus 1 over n appears because now we have the same vector, but we have removed one entry out of the vector because that's the one that we had already found. We continue in that manner, and for the final transcript that we need, so the kth transcript, it takes time, expected time at most 1 over epsilon minus k minus 1 over n. Altogether, this extraction algorithm succeeds in time at most k divided by epsilon minus k minus 1 over n. So all the steps combined. And this already shows that a k out of n special sound interactive proof has knowledge soundness with knowledge error k minus 1 over n. So, and this knowledge error, this result is actually tight. So this is a very simple knowledge extractor for 3-round interactive proofs with this special soundness property. So let us now try to generalize this approach to the parallel repetition and see what goes wrong. So for simplicity, we only consider the 2-fold parallel repetition, but all of this also works for arbitrary t. And now P star is a prover attacking this 2-fold parallel repetition. And if that's the case, then we can see P star, it's still deterministic. We can see it as a function that takes now as input 2 different challenges, 1 for each of the parallel invocations, and it also outputs 2 bit strings Z1 and Z2, 1 for each of the parallel invocations. If you have such a prover P star, then it is quite easy to construct 2 different provers, P1 star and P2 star, that instead of attacking the 2-fold parallel repetition of this interactive proof, they only attack 1 invocation of pi. So P1 star, for example, takes as input 1 challenge. It samples the second challenge uniformly at random. Then it runs this prover P star that attacks the parallel repetition. And it basically ignores the second output of this prover P star. So now P1 star is a prover attacking a single invocation of our original protocol pi. And we can do the same thing for P2 star. Note that in this case, the provers P1 star and P2 star are no longer deterministic. We have this randomness, so they have to sample a random challenge internally. But their first messages are still the same. So this doesn't give us any issues. So now let's take another look at the knowledge extractor. So there's now a very naive approach, simple approach that makes sense to apply the simple knowledge extractor, but now on both the provers P1 and P2 star. The same analysis as before holds, even though the provers P1 and P2 star are not deterministic. However, this approach does not work because we still get knowledge error k minus 1 over n, while our goal was actually to show that this parallel repetition has reduced the knowledge error down to k minus 1 squared divided by n squared. So how do we solve this issue? On a very high level, what we do is we introduce a new figure of merit. So thus far, the figure of merit was epsilon, the success probability of the prover P star. We introduce sort of a punctured success probability delta. And we show that the extractors are exactly the same extractor. We do not modify the extraction approach, but this extractor actually succeeds in time k divided by delta. So now we just refined the analysis of exactly the same extractor. And for the parallel repetition, we managed to show that one of the deltas, so we start with a prover attacking the parallel instance. And from that prover, we can get 2 different provers, P1 star and P2 star. They both have a delta value. And we basically show that one of the 2 deltas is large enough. So, and from there on, our strong parallel repetition result follows. So to go into a little bit more detail, we start with this epsilon, and now we're going to move over to this new figure of merit delta, which is defined as follows. And what you can see here is that delta L of P star is this minimum success probability over sampling the challenges C uniformly at random, but outside of this subset S of size at most L minus 1. So what we do is we take a subset S of size L minus 1, we remove it from the challenge set and see what the remaining success probability of this prover is. And then we minimize over all of these subsets S. So this is sort of a punctured success probability. We remove a couple of challenges that we will no longer consider. And this is actually a very relevant value because it lower bounds the success probability when you are rewinding. Because every time you rewind, you have removed certain challenges from the challenge set that are no longer useful because you have already found them. So then we run exactly the same extractor. We only modify the analysis, and we see that, for example, in the kth step, sampling entries until the kth entry is found takes actually time, expected time at most 1 over delta K of this P star. And altogether, we see that the expected runtime is at most K divided by delta K. So again, the same knowledge extractor, but a different, a more refined analysis thereof. So why is this helpful? It's not going to be helpful if you're only looking at a single invocation of the interactive proof, but it will be helpful if we look at parallel repetitions thereof. So let again P star be a prover attacking the twofold parallel repetition. Then now we can summarize the behavior of P star in terms of this matrix indexed by the challenges. So we have C1 up to Cn. And so the columns correspond to the challenges for the first invocation, and the rows correspond to the challenges for the second invocation of this parallel repetition. And a one entry again corresponds to the prover succeeding for that specific pair of challenges that it receives from the verifier. And now this is basically let us now consider exactly the same matrix, but without loss of generality, we assume that the matrix is sorted. So the rows with the largest number, largest fraction of one entries are at the top, and the columns with the largest fraction of one entries are on the left-hand side. So they are sorted. And if we then look at this matrix, then we can see that this delta K value of P1 star actually corresponds to the fraction of one entries in the blue part of this matrix, because we've basically punctured, we've removed K minus 1, the K minus 1 challenges with the largest success probability, and we only consider P1 star, so we only consider like the first invocation of the basic protocol. And exactly the same holds for P2 star, but then with respect to the rows. So here we see that the delta K of P2 star corresponds to the fraction, or equals the fraction of one entries in the red part of this matrix. So if you take another look at this, then you basically see that if you add these two parts together, then the only part that is not covered is the white part on the left hand corner, left top, which is of size K minus 1 by K minus 1. So that's the only part. So if you look at this, then it's easy to see that the sum of these two delta values, the blue and the red value, is at least epsilon minus K minus 1 squared divided by n squared, where we recall that epsilon is the fraction of one entries in the entire matrix. And from that, it basically follows that at least one of the two delta values is larger than epsilon minus K minus 1 squared divided by n squared over 2. And from this, you immediately get this parallel repetition result, showing that the parallel repetition has knowledge error K minus 1 squared divided by n squared. So the deltas actually allow us to find this relation between the different deltas of the two provers P1 star and P2 star. So in a bit more general, it follows that the default parallel repetition of a k out of n special sound interactive proof is a knowledge sound with knowledge error k minus 1 to the power t divided by n to the power t. So this is a strong parallel repetition result for 3-round interactive proofs that have this special soundness property. Let us now see how we can go to the multi-round setting. So first, there is a natural recursive strategy to go from 3-round interactive proofs to multi-round interactive proofs. However, if you apply that recursive strategy to the above extractor, so to the previous extractor, then you will obtain a runtime that scales exponentially in a number of rounds. So that's not something we want. So what we actually do in the paper is we construct another extractor, which is slightly more involved, but which has better properties that make it amenable for this recursive strategy. So we also have another extractor for 3-round interactive proofs that shows exactly the same result, but that allows you to apply this recursion, this multi-round incursion, to also obtain a strong parallel repetition result for multi-round interactive proofs that have this special soundness property. So to quickly summarize, we introduced a new figure of merit, delta, this punctured success probability instead of merely looking at the success probability, epsilon. This immediately gave a strong parallel repetition result for 3-round interactive proofs. When we go to the multi-round setting, we still had to make some adaptations, but we constructed a novel 3-round extractor for that case as well. And then finally, all of this also works for a threshold parallel repetition, where the verifier does not also accepts if at least, well, so k out of n threshold parallel repetition basically means that the verifier accepts if at least k of the parallel instances are accepting. So it's not required that all of them are accepting. And for all of these results are actually tied. So that means that there is for typical protocols, there is a cheating strategy that succeeds with probability kappa to the power t. So this knowledge error, which shows that you cannot hope for anything better. This was the final slide. Thank you.
So we have time for a couple of questions.
Thanks a lot for the talk. Maybe if nobody else wants to ask a question, I will ask one that I fear is a little bit stupid, but okay. There basically, when you argue that your approach works, then you get this this factor of a half.
Yeah.
But it also multiplies the epsilon.
Yeah.
So why isn't that not a problem?
Okay, let me see.
Maybe go back to your slide.
Yeah, I have to basically have to go back to the definition. So you have this polynomial in the definition that can simply absorb this factor 1/2.
Oh, because this is only about the runtime, not about the success probability.
Yeah. So let's see.
Okay, then answers my question.
Okay, very good.
Thanks.
I have a question that might also be, similar. So what goes wrong if instead of special soundness, but where any 2 transcripts that start with the same messages give you extraction, if you require that soundness be a little bit more structured, so there's some relationships between the 2 C's, what does your analysis, like, I don't see why it wouldn't apply. So
sorry, can you repeat that? So you have 2 interactions.
So some, conceivably, some extraction strategy would say, in order to extract a witness, I need 2 transcripts with the same A and 2 different C1, C2, that, for example, the C1 and C2 differ by, like, have some structure. They, the difference is like a multiple of 2 or something like that. So what goes wrong in your analysis? It might be too complicated.
Okay, so in general, this works, but this is something we're actually working out currently. So that's ongoing work.
Okay.
but there might be some constructions that you can think of if there's like really a strange relation between the two, that's the runtime actually blows up too much.
So it's case by case.
So it depends a little bit on what the relation that you need exactly is.
Right. Thanks. Thanks for the wonderful talk.
Thank you very much.
Speaker. All right. I guess I'll wait a minute. All right. The next speaker is Susumu Kiyoshima with public coin 3 round 0 knowledge from learning with errors and keyless multi-collision resistant cache.
Hi everyone. I'm Susumu Kiyoshima from NTT Research. And today I'm going to talk about my recent work about the public coin 3 round 0 knowledge argument. So I guess many people in this world are already familiar with zero knowledge argument. So I just briefly recall that in a zero knowledge argument, a prover can convince a verifier about the correctness of a statement without revealing anything beyond the fact that the statement is true. And it is called an argument rather than proof, because we only consider soundness against polynomial time cheating prover. And the focus of this talk is a 3-round construction of zero knowledge argument. So as shown in this picture, we only consider construction where the first message is sent by the prover, the second message is sent by the verifier, and the last message is sent by the prover. So 3-round construction are interesting for zero knowledge argument because they are optimal in terms of round complexity due to the classical impossibility of 2-round zero knowledge. However, unfortunately, 3-round zero knowledge is also hard to obtain. And in particular, it is known that 3-round zero knowledge with black box simulation is impossible. So this impossibility means that many of the well-known techniques about zero knowledge cannot be used to obtain 3-round zero knowledge. And because of this difficulty, until recently, 3-round zero knowledge has been obtained only under strong unfalsified assumption, such as knowledge of exponent assumption, or under weaker definition, such as super polynomial simulation security or weak zero knowledge. So this frustrating situation about 3-round zero knowledge has changed recently because of a recent work by Bitansky, Karai, and Panis, who shows that 3-round zero knowledge can be obtained from quasi-polynomial hardness of the learning with errors assumption and slightly super polynomial hardness of keyless multi-collision resistance functions. So clearly, LW is a well-studied, very standard assumption. So what is important about this result is the assumption about the keyless multi-collision resistance functions. So what are keyless multi-collision resistance hash functions? So first, multi-collision is just a simple generalization of the standard notion of collision. And in particular, any collision is a tuple of distinct n elements that are hashed to the same element. Then multi-collision resistance basically says that it is hard to find multi-collision, but it is defined for a bit carefully for keyless hash function so that it is meaningful even for non-uniform adversaries. And in particular, n collision resistance says that any adversary with non-uniform advice of size S cannot find n collision for n that is much larger than S. So basically, this definition says that even non-uniform adversary have some multi-collision as non-uniform input, they still cannot be find any additional multi-collision of much larger size. So more simply, a small multi-collision is useless to find the bigger multi-collision. And for this result of Bitansky et al., it suffices that the n collision resistance holds for some n that is a polynomial in the size S of the adversary. So as you can see, keyless multi-collision resistance has a relatively simple definition, and which is falsifiable. And it's impossible to assume that the real-world keyless hash function like share satisfy this notion of multi-collision resistance. So basically, this result of Bitansky et al. Can be viewed as a result showing that the 3 round zero knowledge can be obtained from simple falsified assumptions. Then, given this result of Bitansky et al., in this work, we show that the public point 3 round zero knowledge can be obtained from almost the same assumption as Bitansky et al.'s protocol. And in particular, we obtain it from sub-exponential hardness of the learning with errors assumption and slightly superpolynomial hardness of keyless multi-collision hash functions. So recall that the zero knowledge argument is called public point if the verifier only sends the outcome of coin toss to the prover, and it computes the final output deterministically from the transcript. So many of the well-known zero-knowledge protocols, such as GMRW and Brown, are public point, but the protocol of Bitansky et al. That I explained in the previous slide is not public point. So public point 3 round zero knowledge is a theoretically very natural target, and this result gives a positive answer about this question. And also, since our protocol is a public point, it automatically satisfies several additional use properties, such as public verifiability, meaning that anyone other than verifier can also check whether a transcript is accepting or not. And it also satisfies leakage regions about verified secret state, since the verifier doesn't have any secret state in a public point protocol. Finally, compared with the 3 round zero knowledge of Bitansky et al., our protocol is a public point, but it is based on slightly stronger assumption. And in particular, it relies on sub-exponential hard LWE, whereas the private point construction of Bitansky et al. Rely on the coarse polynomial hardness of LWE. So this difference of the assumption does not seem very significant, but still it is an interesting question to close this gap between public point 3 round zero knowledge and private point 1. All right, so this is our result. So in the rest of this talk, I will explain our techniques. So basically, our 3 round zero knowledge can be viewed as a public point version of the private point 3 round zero knowledge of Bitansky et al. So let me first recall how they obtain their protocols. So first, they use learning with error assumptions to obtain a primitive called the Oracle memory delegation. So the definition of Oracle memory delegation will be explained shortly. And at this moment, it's suffice to think that it is a very efficient version of interactive argument. Then they use Oracle memory delegation with keyless multi-hash function, keyless multi-collision resist hash function to obtain another primitive called memory delegation. And then they use it with Black non-Black technique to obtain a 3 round zero knowledge argument. Then what is important for our result is that the Oracle memory delegation that they first obtained is a private point. And as a result, the 3 round zero knowledge that they have obtained from it is also private point. Then, given this prior approach, our approach is very natural. So we first obtain Oracle memory delegation, public point Oracle memory delegation from LWE, and then we use it to obtain a public point 3 round zero knowledge argument. And in this talk, we focus on the step of obtaining public point Oracle memory delegation from LW. And I just note that we can use basically the same transformation as Bitan Sakido et al. To convert our Oracle memory delegation to public point 3 rank 0 knowledge. So the goal in this talk is to obtain Oracle memory delegation from LW. So let me first explain what it is. So in Oracle memory delegation, we have a prover and verifier as in a standard interactive argument. But instead of the statement, we have a string called memory. Then the goal of the Oracle memory delegation is that the verifier delegates some heavy computation on the memory to the prover. So in particular, the verifier first sends the function to delegate along with the challenge string to the prover. And the prover evaluates the function on the memory and sends output to the verifier along with the proof showing that the output was correctly computed. Now, an important property about Oracle memory delegation is that the verifier does not receive the whole input as input in the clear, and instead, it is only given an Oracle access to encoding of the memory, and the verifier only makes a small number of queries to the encoding. So this means that even when the memory is very long, the verifier can still be efficient because the verifier does not need to read the entire memory. And in this work, indeed, in this work, we require that the verifier runs in a fixed polynomial time, even when the memory, the length of the memory is super polynomial. And of course, we also have a soundness requirement, which intuitively says that the verifier prover cannot give a convincing answer for incorrect output. So now recall that our goal is to obtain public point Oracle memory delegation from IW. And to this end, we use another primitive called the public point 2 round delegation, which was recently obtained from IW in the name of snag for deterministic computation in the common random string model. So in other words, our approach is to use the recent LW-based public point 2 round delegation as a building block to obtain Oracle memory delegation. So before I explain our construction, let me explain the building blocks that we use. So the first building blocks that we use is the public point 2 round delegation of Jaware, Karai, Kuran, and Chan, or JKKZ, or Holmgren, Lombardi, and Rosbram, or HLR. So the delegation scheme is obtained by applying the Fiat-Shamir transformation to the succinct interactive proof of Goldwasser, Karai, and Rosbram. And the soundness of the scheme is based on the sub-exponential hardness of the learning with errors assumption. And an important property of the scheme is that the scheme has basically the same syntax as Oracle memory delegation. And in particular, the verifier only needs to read a small part of the encoding of the memory. And indeed, it turned out that because of this nice property, the scheme can be easily converted to public point Oracle memory delegation. But the problem is that the scheme works only for limited class of computation. And in particular, it works only for bounded computation with a certain form of succinct descriptions. So what we need for our purpose is the Oracle memory delegation for all slightly superpolynomial computation. So even though the scheme can be converted to Oracle memory delegation, unfortunately, the scheme alone is not sufficient for our purpose. So in this work, we also use another building blocks, which is the public point 2 round delegation of child Furi, Jane, or Qing, or CJJ. So the scheme is based on slightly superpolynomial hardness of the learning with errors assumption when it is used for slightly superpolynomial computation. And just like Oracle memory delegation, the scheme does not require the verifier to have the entire memory as input. And in particular, the scheme only requires that the verifier has a macro hash of the memory, where the hash function, the underlying is chosen by the verifier. Now, a good point of the scheme is that it works for all slightly superpolynomial computation. But the problem is that even though the scheme does not require the verifier to have the entire input, still it is not clear how the scheme can be converted to Oracle memory delegation. So in particular, the problem is that it is not clear how the verifier can obtain the mark hash of the memory in the setting of Oracle memory delegation, where the verifier can only make a small number of queries to an encoding of the memory. So in summary, we have two delegation schemes. So the first one can be converted to Oracle memory delegation easily, but it works only for a limited class of computation. And on the other hand, the second one works for all slightly superpolynomial computation, but it cannot be converted to Oracle memory delegation. So neither of them alone is sufficient for our purpose. Now, given this situation, our approach is very natural. We combine these two delegation schemes to obtain public Oracle memory delegation for all slightly superpolynomial computation. So finally, I'm ready to explain our construction. So the first step of our scheme is that the prover uses the delegation of JKKZ and HLR to prove the correctness of macro hash computation of the memory. So in particular, the verifier sends the hash function along with the challenge string to the prover, and the prover computes the mark hash of the memory and sends it to the verifier along with the proof, showing that the macro hash was correctly computed. So recall that the delegation of JKKZ and HLR can be converted to Oracle memory delegation easily. So this step of a scheme can be done in a way that the verifier only makes the Oracle query to an encoding of the input, encoding of the memory. And also, even though the scheme works only for a bounded depth circuit with a certain form of succinct description, it turned out that the scheme can be used for macro hash computation. So I won't explain the technical detail about the reason for this, but the point is that simply that the macro hash computation can be described very succinctly. So in particular, we can obtain circuit for macro hash computation by just combining many copies of small subcircuits that compute the underlying hash function. So given this succinct description of macro hash computation, actually it is very easy to observe that the delegation scheme of JKKG and HLR can be used for macro hash computation. Now the second step of our scheme is that the prover uses the delegation of CJJ to prove arbitrary computation on the memory. So in particular, the verifier sends a function to delegate along with the challenge string to the prover, and the prover evaluates the function on the memory and sends it to the verifier along with the proof, showing that the output was correctly computed. So recall that the CJJ delegation scheme works for all slightly superpolynomial computation. So indeed, in our scheme, the prover can use it to prove any arbitrary computation on the memory. And also, even though the CJJ delegation scheme requires that the verifier has the macro hash of the memory, we can still use it in our scheme, since in our scheme, the verifier obtains the macro hash of the memory from the prover. Now, basically, the soundness of our scheme follow very naturally from the underlying delegation scheme, and in particular from the soundness of the CJJ delegation scheme, because the macro hash that the verifier obtains from the prover is guaranteed to be correct because of the soundness of the delegation of the JKKZ and HLR. So in this way, we can obtain a public Oracle memory delegation from LWE. And as stated earlier, we can transform it to public point 3 round zero knowledge by using the non-transformations. So in particular, people who are familiar with Black's non-Black technique can think that the memory delegation that we obtain from Oracle memory delegation can be used as a universal argument in Black non-Black technique. And since the memory delegation has only 2 rounds, we can reduce the Black non-Black technique, but you can reduce the round complexity of Black zero knowledge to 3, so we can obtain public point 3 round zero knowledge. So in conclusion, in this work, we show that the public point 3 round zero knowledge can be obtained from simple falsifier assumption. And in particular, it can be obtained from sub-exponential hardness of the learning with errors assumption and the slightly superpolynomial hardness of keyless multiple reduced hash functions. So an interesting open question is to weaken the assumption of our result, and in particular, weaken the assumption about LWE from sub-exponential hardness of the LWE to the corresponding hardness of the LWE. So if we can do this, we can close the gap between public point 3 round zero knowledge and the private point 1. And another more ambitious open question is to obtain 3 round zero knowledge from more standard assumption. So in particular, keyless multiple reduced hash function is a relatively new hardware assumption. So it will be good if we can obtain 3 round zero knowledge from other primitives that are more standard than the keyless multiple reduced hash function. Yeah, and this concludes my talk. So thank you for the.
Thanks. Thank you very much for the wonderful talk and fantastic result. We have time for a question if anybody has a question. If nobody has a question, I have a question. Okay, I'm going to ask my question. So my question is, in your roadmap on slide 15, what parts of it actually need LWE and what parts of it are just general enough that if you're given these building blocks, you can get the same result? Sorry. On slide 15, why do you need LWE?
Why? So the question is why we need LWE from here.
Yeah.
That's because we currently have only public. The only construction that we have from public point Oracle memory delegation is from LWE, and in particular, it uses like FHE or some kind of construct.
So if you could swap another construction of public coin to run Oracle memory delegation and another construction of public coin to run memory delegation,
yeah,
then it would. So basically, your transform is general.
Yeah.
It's just that the building blocks need LWE.
Yeah, exactly.
Okay, thanks. Let's thank the speaker again.
Okay, is the mic's on? Cool. What? Can I start?
Okay, so the next the next talk the next talk is Faster Sounder Succinct Arguments in IOPs by Justin Holmgren and Ron Rothblum, and Justin will give the talk.
Thank you. Yeah, so I thought I should start by maybe explaining how to parse the title. Oh, that's the wrong version of the slides. Ugh. Okay, well, we'll see. It'll be fun. So we're all in the proof system session. I assume we all love proof systems. If not, I'll try to convince you very quickly that you do. So proof systems are this amazing success story in theoretical computer science. Really amazing. You know, it started out in the 80s. Nobody thought any of this would be practical, but we kept evolving the notion of a proof. We started with NP proofs, interactive proofs, and then this whole thing blossomed. And they led to other related notions that now we think of as very central, like the theory of NP completeness, zero knowledge, PCPs. So there's this theoretical side of proof systems, but also I've heard that recently they've started to have some real world applications. I've never implemented a proof system in my life, but I think this person has, and he says that succinct zero knowledge proofs are very useful. However, one of the major barriers to further deployment of proof systems is the prover efficiency. So in practice, proving is much slower than just doing a computation with no proof, which is the best you could hope for. And so there's a natural question of like, how inherent is this gap? Can proving be as fast as computing? And so we're going to look at pretty small factors here. And so I want to be pretty precise about what computational model we're using to measure complexity. And we're using Boolean circuits, which I think are the best, most natural computational model. They're super just natural. I think they very closely match the physical cost of implementing something in hardware. And there are a lot of computations that we might want to delegate or might want to prove stuff about. For example, these sort of mini crypt-like hash functions that are not by default nicely arithmetizable. So that's the alternative to Boolean circuits that people often study in proof systems, is like arithmetic circuits over larger fields. So when we talk about the prover complexity in this talk, we're talking about a cost that's parameterized by two inputs. So first of all, there's the size of the circuit that the size of the computation that you're trying to prove something about, and then there's the soundness error, the probability of a verifier accidentally accepting an incorrect statement. And usually think of the soundness error as exponentially small in something called the security parameter. And the security parameter is usually somewhere in between, like the log of the size of the computation and much smaller than the entire computation, than the size. So just to survey some of the previous work, there was a recent breakthrough by Ronzulli and Rothblum that showed how to prove the satisfiability of Boolean circuits with a complexity that was proportional to the size of the circuit and the security parameter. So this dependency on the security parameter comes from basically parallel repeating. The basic protocol gives constant soundness error, and they repeat lambda times. So that's where the factor of lambda comes from. On the other hand, if we're in a setting where you have an arithmetic circuit over a large field, so actually bigger than what I said, but not too much, like an exponentially large field, then you can have a proof system in which the prover's complexity is basically linear in the size of the computation. So yeah, in our work, we sort of improve on this. We reduce the dependency of the security parameter from linear to polylogarithmic. So I guess you can call it an exponential improvement if you like. There's one caveat that this only holds for nice Boolean circuits, which I'll elaborate on what I mean by nice, but you can think of it as just having some kind of repetitive structure. I guess I'll elaborate on it now. Okay, so here are some simple examples first. And the technical definition that we use is kind of messy and full generality. So first of all, one type of nice circuit is a circuit that has a sort of batch structure. So to evaluate the circuit, you just evaluate one circuit many times on different parts of the input and then hope that they all evaluate to one. Another example of what I would call a nice circuit is an iterated circuit where you apply a circuit sequentially to some input. So you feed the output of one iteration into the input of the next. And nice is sort of a quantitative notion here. Our basic verifier in our like straightforward or core construction has complexity that's proportional to the sort of repeated structure here, but it can you can compose with other proof systems to get that down basically as much as you want if you're lucky. There is a more general definition. Yeah, but I just won't get into it now, but I'm happy to talk to you about it later if you'd like. So actually, I'm just going to download the new slides. It'll take like 1 minute and I'll be much happier. Yeah, I downloaded them before. I don't know why they Oh, I see. Okay. Oops. Download them. Oops. How do I make full screen? Okay, well, I will do it like this. Work. All right, here we go. Sorry about that. Yeah, so here's a sort of TLDR result after all interruptions, sorry. So we get a succinct proofs where the prover complexity is the circuit size times the polylog factor in the security parameter. And I'm not going to worry about the additive polynomials.
You need to share your screen on Zoom.
Oh, I do?
Yeah, and
Okay.
and we need, I think, wait, are you already sharing it?
Yeah, it says
'Cause
sharing.
that's weird. Because what
Sharing, you need to go full screen. It's the arrows that are pointing in opposite diagonal directions.
Oh, yes, that's right. You're sharing the other screen. That's right. Yeah. You need to
see.
share this window instead of the other one.
Can you show me what to do?
Yes, stop share. Mhm.
All right.
And then go back to your Zoom, back to Zoom.
And
And
share.
share screen and then share the correct slides.
Okay. All right.
Thank you.
Yeah. Is this okay for people on Zoom?
Yes.
So, great. So just to put the result in context again, next to the other results. So the best thing we would hope for this polylog to go away and just have O of S plus lambda. We don't quite get that. All right. So now I'm going to talk a little bit about like what the sort of main lemma is in our work, and it's not 100% technically accurate, but I think it captures the new contribution sort of. So we show that there's a linear code that we can encode in with overhead polylogarithmic in the security parameter. And given encodings of 3 vectors x, y, and z, you can prove that z is a pointwise product of x and y with soundness error 2 to the minus lambda. And sort of assume here that you're given these encoded vectors in the sense that the verifier can make whatever random access queries it wants to them. And it knows that these things are properly encoded, but it doesn't know what the encoded values are. Right, so that is the result. And now I'm going to sort of delve into the techniques a little bit. It's a little technical, but first I want to sort of say what the prerequisites to this result are, the things that we build on. Let's start with the simplest thing. We use a small finite field, so finite field of order security parameter. So not the exponential dependence. We build on some good error correcting codes. So in particular, we'll use 2 types of codes. The first is kind of a heavy hammer from the previous work of Runsley and Rothblum at this past stock, which has 2 salient properties. The first is that it's sort of linear time encodable, and it'll solve this task that I wanted to solve, this pointwise Hadamard check, with a constant overhead and constant soundness error. So this sort of illustrates that you could get the 2 to the minus lambda soundness error by just repeating, but that would kill the constant overhead. So we don't want to do that, but we will still use this as part of our solution. And the second code, which is probably much more familiar, is just good old Reed-Solomon codes, or and more generally, multiplication codes. And Reed-Solomon codes have the nice property that they're encodable in quasi-linear time, and using fast Fourier transforms. All right. So this is the last really technical slide, and I want to talk about how we put these ingredients together to get our core lemma. So the first step is to take these vectors that we want to prove a pointwise product constraint on and view them as matrices. And our encoding will be sort of left and right multiplication by these different code generator matrices. So what that looks like, the way we view our X as a matrix is, despite what the picture would have you believe, all the matrices here are really tall and skinny. So there's layout constraints. Or I've heard that the camera adds 10 pounds or something. So anyway, so the width of X is lambda, the security parameter, and the height is the original size divided by that. And so we encode all the rows of X with a Reed-Solomon code. That's this right multiplication by M. And then we take each column thereof and encode that with the code from RR22. Yeah. So this is basically, I mean, another way of saying this is a two-dimensional tensor code. And anyway, we sort of start with a similar encoding of Y and Z. And now we want to get to work proving that that Z is, yeah, there should be a little box that says Z in the same position. We want to prove that Z is the pointwise product of X and Y. So the first thing that we'll have the prover do is send a matrix that's kind of like halfway between, so like almost what Z hat should be. So they take the top half and do the pointwise products of X hat and Y hat, and then do a column-wise encoding with this RR22 code. And you can kind of do some consistency checks here. I don't really want to get into the details exactly, but you first do you sample a random column and you check that you basically are able to check that Z tilde encodes the pointwise product of the corresponding message parts of X hat and Y hat. And the second thing you need to show is that what's in Z tilde is actually the same as what's in Z hat. So those are under different codes. So that's sort of a code switching step. Now, for this basic step, we just get a constant soundness error. And I am going to suggest that we repeat this lambda times to get our 2 to the minus lambda soundness error. So why is this not an issue like it was in all the previous works? So the point is that we've reduced to checking a smaller claim. Before we had to check the pointwise product of X, which was this thing of size n, but now we're checking just lambda columns, which in total have size n. So if each one of those has a constant probability of detecting an error, we'll get our 2 to the minus lambda soundness error, and our total running time will still be O of n. And the checking the rows here, because remember these are actually tall skinny matrices, checking the random rows is really, you don't need anything special. You can just do this directly. It doesn't cost anything. All right. Well, I think I'm done with that, and I will propose possible sequels to this work. So one is, as I mentioned earlier in the talk, to just improve the prover size further. This is sort of the best that we can imagine now. One way to do this would be, so you can imagine something like a Reed-Solomon code where the encoding is not quasi-linear and is just linear size. If you could do that, you'd be done. You'd get this result, and I'd be very happy. But this is an open question in coding theory. I don't know if it's gotten so much attention that you should expect this to be an impossible problem to solve, but it does seem challenging to me. Another interesting open question is to make this whole scheme non-interactive, or to get any scheme that has a similar polylogarithmic security parameter overhead from a standard assumption. So right now you can take the scheme and Fiat Shamir, plug it with it, and prove that it's secure in the random oracle model, I think. But maybe if you don't like the random oracle model, you might be interested in doing it from a full survival assumption. Finally, there is this whole issue of the nice circuits. One could definitely hope to handle arbitrary Boolean circuits, especially if the verifier is doing some pre-processing. That's the last open question for now. And if you would like to look at the nice version of the slides, you can scan this QR code or the paper, or you can find it on ePrint, the website. All right, and it looks like maybe there's some questions in the chat, or maybe complaints about. Oh, okay. No, no questions, I guess. Or any questions in the audience?
Oh, you have a question. You have a question. You have a question.
Hey,
Oh.
thanks. Thanks. That was a great talk. The question is, like, can you say some more about the way that the size of D, that circuit that was, sort of the thing that you use to define the structure? How does this reflect to the final complexity of the proof?
Final complexity of the proof. So if we start with a proof system which the verifier, the only like annoying overhead is the verifier runs in time proportional to D. You could imagine, instead of having the verifier actually run it, the prover convinces the verifier that it would have accepted. So the prover's complexity then is D times some small factor, but if D is smaller than the whole circuit, then that's like negligible.
Right. Okay, thanks.
Any more questions? Thank you very much.
Can you hear me? Yes, you can. I'm supposed to waste one more minute, but I don't have any jokes ready, so.
Yeah, so this talk is scheduled to begin at 3:05. And we are, you know, we're going to be back on schedule. Because I don't want people to miss it because we start early.
I believe it is the session chair's responsibility to tell the jokes to pass the time.
Okay, so here's a joke. I lost my voice. I have laryngitis, so I cannot tell jokes.
I accept your excuse.
Okay, it's 3:05 now. So the next paper is Succinct Interactive Oracle Proofs, Applications and Limitations by Shafiq Nassar and Ron Rothblum, and Shafiq will give the talk.
Thank you for the introduction. And I would like to thank the previous speakers for warming you guys up and defining things so that I don't have to define things anymore. So this talk is about Succinct Interactive Oracle Proofs. So let's start by breaking down the title, understanding what we're talking about. So of course, the first click never works. Yeah. So interactive Oracle proofs, or IOPs, they're this relatively new type of proof system that generalizes both traditional interactive proofs and probabilistically checkable proofs. So how do they work? We can think of them as an interactive proof where the verifier only has Oracle access to the prover messages as opposed to the full access that it would get in a traditional interactive proof. Or alternatively, we can think of it as an interactive analog of a PCP. So a PCP is basically like a round or half a round IOP. And just to give an illustration, we'll be talking about public coin interactive Oracle proofs. So basically, we have a verifier and the prover. The verifier's messages only consist of randomness that it sends publicly to the prover, and the prover responds with those messages. And this is the interaction phase. After the interaction phase is done, based on the randomness of the verifier chooses a small number of queries from the messages that the prover sent, makes those queries, and decides accordingly. So we have the usual requirements of completeness and soundness. And just to establish some notation, when I say communication complexity denoted by CC, I am referring to the total length of the prover messages. So I'm not counting the verifier messages. Those are counted towards the randomness complexity, which we denote by RC. And finally, the query complexity is the number of queries that the verifier makes at the end. Okay, so this is an IOP. What are IOPs good? What are IOPs good for? That's a legitimate question. And IOPs have many applications. So from constructing succinct arguments to delegation of computation, even more recently, they've been used to achieve hardness of approximation results. So IOPs are very useful. They have many applications. But before we talk about applications, let's ask an actual question about IOPs. So even about PCPs, when we're talking about an IOP or a PCP, they basically provide a mechanism that allows us to encode a witness or computation in a way that allows the verifier to check or verify the correctness of the statement by just looking at small number of locations in the encoding. And it's a very natural question to ask, how short can this encoding be? So if we go back to the original proof of the PCP theorem, there the length of the PCP proof was polynomial in T, where T is the verification time. And many improvements have occurred since, and now we have PCP proofs with quasi-linear length. But an interesting question here is, can we get close to the original witness? That is, can the encoding only depend on the original witness rather than depend on the computation or the verification time that we have to do afterwards? And this brings me to the first word in the title, which is succinct. So a succinct proof basically means a short proof. Namely, when we're talking about NP relations, a succinct proof is a proof whose length is polynomial in the witness rather than the instance. And why is this good? Because for typical NP relations, we think of the instance as being much larger than the witness. So if we have a succinct proof, then basically we have a shorter proof. That's good. We like short stuff. We like efficient stuff. And again, we might ask if there exists succinct PCPs for all languages in NP, for example. And unfortunately, we know a negative result by Fortnell and Santanam. They showed that under a standard complexity assumption, there is no succinct PCP for SAT. On the other hand, we know that there's a succinct IOP for SAT. In fact, we know a couple of constructions. So first of all, let's take a minute here to appreciate that basically this shows a separation between PCPs and IOPs. An IOP can do something that we believe a PCP cannot. Now, let's ask another question. We have a succinct IOP for SAT. Does this imply a succinct IOP for all NP relations? After all, SAT is an NP-complete problem, so we can reduce any other problem to it. But unfortunately, no, because reductions do not necessarily preserve the witness length. So even if we do the reduction to SAT, we're losing all succinctness because the new witness can depend on the original instance instead of just on the original witness. So this leaves the question wide open. Is there a succinct IOP for all NP relations? Now, the previous slide is supposed to motivate the study of succinct IOPs because, it's a natural question. It's interesting from a theoretical perspective, but some people might ask about applications. And like if we look at one of the main applications of IOPs, which is constructing succinct arguments, there we know that communication complexity is not actually the bottleneck because we're applying this Killian style Merkle hashing and we eventually compress the communication. It doesn't really do that much overhead. So even if we improve the communication complexity and get a succinct IOP, we won't significantly improve the succinct arguments. So what are succinct IOPs good for? So this brings me back to the title and I'm going to show an application. So this is our first result, basically, showing an application for succinct IOPs. We present a compiler that takes a succinct IOP and transforms it to a succinct zero-knowledge proof. And I have to emphasize here that we're talking about a proof, not an argument. So we have statistical soundness, which means that soundness holds even against an unbounded cheating prover. And this is as opposed to arguments, which is the focus of the previous work on IOPs. And this compiler only needs the assumption or minimal assumption of one-way functions. So give me a one-way function, that will give you this compiler. There's no need to bring in the big guns here or any other more sophisticated cryptographic assumptions. So this is our first result, and set zero-knowledge proof. So I have to just remind you guys what zero-knowledge proofs are. So basically, a zero-knowledge proof is an interactive proof where the verifier learns nothing when interacting with the honest prover, other than the fact that the instance is indeed in the language. And the state of the art on succinct zero-knowledge proofs prior to this work is the following: assuming full-fledged, fully homomorphic encryption, so bringing in the big guns, we get something that is essentially optimal. We get a zero-knowledge proof for all NP relations, where the communication complexity is basically the length of the witness plus some additive factor that depends on the security parameter lambda. On the other hand, if we're assuming one-way functions, then we get a zero-knowledge proof for a subclass of NP relations. It can be verified in bounded depth. And here, the communication complexity is the witness length with a multiplicative factor that depends on the security parameter and logarithmically on the instance. So we have this gap here. What we have with fully homomorphic encryption is basically a zero-knowledge proof where the communication approaches the witness length. And here we don't have that. Still, it's succinct, but it's multiplicative. Like we have a multiplicative factor. If we take our compiler and we apply it to the succinct IOP of Ronsley and Rothblum, we get the shortest known zero-knowledge proofs for bounded space NP relations under the minimal assumption of one-way functions. So basically, what we get is a zero-knowledge proof where the communication complexity is this thing over here, which is something that approaches the witness length, plus this additive factor that depends polynomially on the security parameter and the power of the instance. But the thing is, this power can be arbitrarily small. So any small constant here can be plugged in, and we get the length of the instance to the power of that small constant. So in a way, this is approaching the witness length. So this is how our result compares to the previous stuff. So assuming one-way functions, we get zero-knowledge proofs for, again, a subclass of NP relations that can be verified in small space, but we have at least something that is approaching the witness length. So hopefully by now I've convinced you that succinct IOPs are cool, they're nice, they're useful, we can use them to do stuff. And it's interesting if we can go now beyond bounded space. So we know that there is a succinct IOP for SAT, for example, or a succinct IOP for relations that can be verified in bounded space. And this implies succinct zero knowledge proofs. And we'd like to get a succinct zero knowledge proof for all of NP under the assumption of one-way functions. So this brings us back to the question, is there a succinct IOP for all of NP? And when we wanted to approach such a problem, it's good to look at the previous results or previous techniques and try to apply them here, because an IOP is a generalization of both interactive proofs and PCPs. So maybe we can use the limitations or the techniques that are applied to those things on IOPs. And for IOPs, for interactive proofs, this basically doesn't work because there's no such limitation. We have a trivial succinct interactive proof for all NP relations. We can simply just send the witness. So there's no such limitation. If we try to take the Fortnow-Santanam technique that I talked about earlier, then it also wouldn't work here because it rules out succinct PCPs for SAT. But we do have a succinct IOP for SAT. So at least if we want to use that same technique as a black box, it won't work here. So we need to do something else. So this brings me to the second result that we have, and this is like just the short version. Under a new but reasonable complexity conjecture, at least I think it's reasonable, we prove that there is no succinct IOP for all of NP. So there is some relation that has no succinct IOP under this new complexity conjecture that I'm going to talk about in a bit. The main ingredient in proving this is, again, presenting a compiler for IOPs. So this compiler takes a succinct IOP and produces a special sort of algorithm that we call a small space algorithm with pre-processing. So it's basically a pair of algorithms, A1 and A2. I'll just take a moment to explain what that is. So we say that a language L can be decided in S space with T time probabilistic pre-processing. There exist two algorithms, A1, the pre-processing that runs in that time, and A2, the small space algorithm. It can decide the language. And how does it work exactly? So we take our input, we feed it to the pre-processing algorithm. This gives us an intermediate instance that we feed to the small space algorithm, and then the small space algorithm either accepts or rejects. So again, if we go back to our compiler, we take a succinct IOP and we produce this sort of algorithm that decides the same language that the succinct IOP decides. And of course, we have the regular requirements of completeness and soundness. And just to put parameters on this thing, so our compiler works as follows. If you give me an IOP that has communication CC, communication complexity CC, number of rounds is K, query complexity is QC, then the space of the algorithm is basically proportionate to the communication. It's just CC plus K times log CC. And the pre-processing depends exponentially on the query complexity, but that's okay because it's an IOP and we typically think of the query complexity as being very small. Polynomially on the instance, that's also okay. And we have this thing over here. This is the most annoying thing, but it's here. It's 2 to the K log CC. So we're talking about succinct IOPs. Let's just try to put some parameters in here to try to understand how this thing really works. So if we talk about succinct IOPs, so the communication is polynomial in the length of the witness. And let's assume that the number of rounds is constant and the queries are logarithmic. Sorry about the colors, by the way. They appeared better on my computer. So this is the rounds is constant and the queries are logarithmic. Then we get an algorithm that decides L where the space is polynomial in the witness and the pre-processing time is polynomial in the instance. Okay. And let's think about this sort of algorithm for a bit. So this is supposed to lead to the complexity conjecture that we present in this paper. So when I say succinct space, it's like succinct proof. I'm talking about space which is polynomial in the witness. So it only depends on the witness and maybe it depends logarithmically on the instance as well. And for example, we know that SAT can be solved in succinct space. So when I'm talking about SAT, I'm talking about deciding whether a CNF formula is satisfiable or not. And this can be done in succinct space. Why? Because we simply need to iterate over all of the assignments. For each such assignment, we iterate over all of the clauses and verify if they're satisfiable or not, if they're satisfied by the assignment or not. So basically, the space that we need here is exactly the witness plus log of the instance. On the other hand, there's a generalization of SAT called circuit SAT, which seems to require more than that. So just to clarify, circuit SAT is the language of Boolean circuits that are satisfiable. So a formula is like a bounded depth circuit. When we're talking about a general circuit, it can have more depth. And circuit SAT seems to require space which is proportionate to the size of the circuit, not just the witness or the input of the circuit or the assignment. In fact, just evaluating a circuit on a certain input is believed to require space which is proportionate to the circuit size. So now if we go back to the algorithm that we got from the Succinct IOP, it gives us probabilistic polynomial time preprocessing and small space, succinct space, basically. Oops, succinct space. And the question is, will this be enough? If I give you probabilistic polynomial time preprocessing, will succinct space be sufficient to decide the circuit SAT? Now, let's think about the two extremes. If we don't do anything in the preprocessing and we just try to do all of the computation in the succinct space, then we run into this problem or this conjecture over here. And on the other hand, if we don't do anything in small space and try to do everything in PPT in the preprocessing phase, then again, probably won't work, right? So I believe that no one here believes that we can solve an NP-complete problem in PPT. So the conjecture here is just a generalization of those two extremes. It says, if I give you both, can you do this trade-off between time and space and get something interesting? And we conjecture that this is not doable. So our conjecture says that if we give you a space that is polynomial in the assignment and probabilistic preprocessing, which is polynomial time in the size of the circuit, we still can't decide circuit SAT. And given our compiler from before, we conclude that under this conjecture, there is no constant route succinct IOP for circuit SAT, where the query complexity is logarithmic. And yeah, basically the number of rounds is constant. So this is the second result that we have. I have a reminder here of the compiler. So these are our two results. So the first one is an application. We get zero knowledge proofs from succinct IOPs. And the second one is this a lower bound assuming the new conjecture. How much time do I have left?
You have a lot of time. You have 8 minutes.
8 minutes?
With questions. So
yeah, I see. Okay. I thought that this would take the entire time here. So I can just talk about open questions and then maybe I can dive a little bit into the techniques. So one of the open questions is, can we get rid of the, if we go back here, it does go back. Can we get rid of this power of the instance, even though it's like arbitrarily small power, but still we'd like to get a truly succinct zero knowledge proof and get rid of this thing. So that's the first question. The second question is, can we get the opposite of our compiler? So our compiler takes a succinct IOP and converts it to a small space algorithm with preprocessing. And it would be interesting to turn this into an if and only if kind of statement. So if we have a small space algorithm with preprocessing, can we turn that into an IOP? Actually, we can, but the number of rounds would grow a lot. And it would be interesting to get the same number of rounds that we get in both directions. And another open question is whether we can base our conjecture on other known conjectures or give more evidence to our conjecture that there's no succinct IOP for CSAT or for all NP relations. Any questions?
Well, I have a question. Can you say more about the application?
I'm sorry?
Can you say more about the application of IOPs, of succinct IOPs? Your first result.
Yeah, I can delve into the technique of.
Yeah.
Okay, so I'm a bit ready. So how do we construct succinct zero-knowledge proofs from IOPs? So basically, we're using here standard techniques that were known before for interactive proofs, and we're just appropriating them to IOPs. So the first technique that we use is the notarized envelopes technique. So basically, what it says is that we can do an encrypted interaction, an encrypted version of the interactive proof. So this heavily depends on the fact that we have a public coin protocol. So the prover, instead of sending its messages in the clear, it sends a commitment of those messages. And the verifier responds with the public coins, because it doesn't matter. It doesn't read the messages before replying with public coins. And in the end, we'd like for the prover to reveal its messages so that the verifier can decide whether to accept or not. But instead of doing that, we prove in zero knowledge that if the prover did indeed reveal those messages, then the verifier would accept. So basically, the NP statement that we prove at the end is that there exists a decommitment such that the revealed messages would make the verifier accept. So this is the first technique that we use here. We have like a zero knowledge proof at the end. The thing is, we can utilize the fact that we have an IOP instead of an interactive proof. And basically what this means is that the verifier is interested in just a small number of the locations in the prover messages. So the prover doesn't have to reveal everything. The statement can only correspond to the small number of locations in the prover messages. So if we use like a commitment with local openings, then the zero knowledge proof at the end can be much shorter. So this is the second thing. And basically how we use the kind of commitment that we use is just a PRF. So basically the prover at the beginning commits to a PRF seed, sends it in this box, and then uses the PRF with this seed to pseudo-random one-time pad its messages. And in the end, it just, the end statement only depends on the seed, on this little box that has been sent, and the specific locations. So this is the second improvement we do to the notarized envelopes technique. And the final thing is that the final issue here is that still the verification that we need to do depends on the statement on X. So even if we had succinctness at the beginning, we're losing all of this we're losing this succinctness in the final stage of the zero knowledge proof, because the verification can be polynomial in X. Yeah, those should have been here before. Sorry about the transitions. So the thing the final piece here is we're looking at non-adaptive IOPs. So a non-adaptive IOP is an IOP where the the queries of the verifier don't depend on the values of previous queries. It just depends on the randomness and on the instance itself. So after the communication phase the interaction phase is done, the verifier just chooses all of the queries that it wants to make in the spot, and it makes those queries and doesn't change anything about them. So that's the non-adaptive thing. And we say that, and then on those queries, it applies this sort of predicate and just decides accordingly, according to the value of the predicate. And we say that the verifier is gamma compact if the size of this predicate is at most gamma. And it's easy to see here that the final NP proof doesn't have to depend on X. It only depends on the compactness, on the size of the predicate, because once we know the randomness and we know X, we just need to generate this predicate. And the statement is whether there exists a decommitment that would make this predicate output 1. So if the IOP that we have is very compact, then the zero knowledge proof that we have at the end is going to be very small, and we actually prove that the IOP of Wronski and Rotem is indeed very compact. So we get the zero knowledge proof to be very, very short here. So these are basically the ingredients to a proof: just your favorite zero knowledge proof for NP, a statistically binding commitment scheme, and a pseudo-random function, and all of those we can get from one-way functions. And that's the protocol, but I've already talked about that. There's no other thank you slide. So I have to go back to that one. But thank you.
Thanks a lot. So this is the end of the, well, actually, if you have more questions for the speaker, since this is the last one, you can still ask, but this was the last one. Go ahead.
Hey, Shafiq, nice results, great talk. You had a slide which said that with FHE, we can get proofs that approach the witness length. And with one-way functions, you have this annoying additive factor floating around. I was wondering whether somewhat homomorphic like encryption, does it give you something better?
Again, so what's the question again?
Yeah, so you had a slide which said that with FHE.
I'm trying to get there, but yeah, I can ask a question. Wow, this is slow.
No, it's.
Yeah, so with FHE, you can get these proofs which approach the witness length.
Yeah.
With one-way functions, in your result, you have that annoying additive factor, right?
Yes.
And I was wondering whether like some weaker form of FHE, which is somewhat homomorphic encryption, does that allow you to get something better?
I'm not sure I understand the question. Like FHE gives us this.
Right, so does any weaker form of FHE, like somewhat homomorphic encryption or...
Sorry, I just can't hear you.
So for example, does additive homomorphic encryption give you something
additive
better?
homomorphic encryption. That's the word I've been missing the whole time. I'm not sure. I haven't thought about it. I really don't know.
Okay, no
Sorry,
worries, thank
all
you.
of that make you repeat the question just to tell you I don't know. Yes.
Yeah, I was wondering whether you thought of maybe basing the impossibility result on like some sequential computation, like say a hash chain even, or in some style in some random oracle model, right? It seems very unlikely that I mean, in the random oracle model, it's probably impossible that I can get a succinct TCP IOP anything for say a hash chain, even though it has a very, very short witness and even the instance is short. Have you thought about basing it on sequential computation? Oh, okay. So you can actually. Oh, interesting. Okay. So this I can say with Nova.
I think
so the answer is it is actually possible, but runs.
Thank
It's
you.
not
Ron, for
impossible.
bailing me out again.
Thank you very much. And it's fun.